Before we start tackling any of the challenging problems you can solve with graphs, like the ones we described in the previous video, we're going to talk about different ways of representing a graph in terms of more elementary data structures. So I'll start by saying that a common convention is that instead of, say, creating a graph of Austin, Dallas, Houston, we'll create a graph which will have integer vertices, similar to what we did with disjoint sets. And throughout the implementation, we'll think about our vertices as purely numbers. Now, if you want a graph that represents something like cities, then we might imagine having a map from string to integer, and maybe another from integer to string, so that we can say, okay, whenever I say Austin, I mean 0, when I see Dallas, I mean 1, and so forth. And if you want to go the other way, which you would just create the other map as well. Okay, so given that fact, this is what our API for graph is going to look like. Remember that API is just a term we use to indicate the interface. So application programming interface is what it stands for, but that's API. So using a graph in Java, this is the version from our optional textbook. It has a few methods. We have add edge, we have edge, we have v, we have e, and we have a constructor. So what do each of these do? Well, with a graph, we're going to assume that our graph has a fixed number of vertices. Now, that of course is something you might not want. You can make a more complicated graph implementation if you'd like, but for our purposes, we're going to say it has a fixed number of vertices. We can then have an add edge method that will create an edge between v and w. We have edge, which will return all of the vertices that are adjacent to something. So for example, if we pick 0, it'll give me back 1 and 2. We'll have the number of vertices v, and we'll have the number of edges e. Okay. So here's an example client. Let's say I have this undirected graph here, and so I guess for now, let's consider only the undirected graph case. This is an undirected graph, and let's suppose we write a method called degree. So degree is a graph term I haven't introduced, but it basically just says how many edges are incident on that graph node. So if I say, hey, here's a graph, here's a vertex, tell me how many edges it has, the way it works is we'll first say the degree is 0, then we'll go through each of the adjacent vertices to v. So in this case, if we call it on 2, the adjacency iterable will contain 1 and 3. We'll add 1 to degree twice, and we'll return degree, which will be 2. So that's an example of the kind of thing we'll be able to do with graphs using this simple API. Now, it may be that you want a more complicated API that involves adding vertices and whatever else, but for our purposes in this course, we're going to stick with a simple graph API, and you can go beyond that if you'd like in the future with natural extensions. So let's talk about different representations for a graph. If we actually want to talk about how these graphs are represented in terms of basic data structures, the first one might be something called an adjacency matrix. Okay? This is the most obvious way to represent a graph, arguably. And in it, we basically create an n by n array, or sorry, a v by v array, which indicates how many or whether an edge exists or not. So for example, this graph here, 0, 1, 2, our adjacency matrix, it will look like this. There exists an edge from 0 to 1, from 0 to 2, and from 1 to 2. Those are the only 3 edges. In undirected graph, we can use the same idea. And I'll just note that the common convention is that we'll actually include each edge effectively twice. So in this case, there's an edge from 0 to 1. Okay, so 0 to 1, and also an edge from 1 to 0. So that's just usually what we do in terms of representing undirected graphs. You could do it differently if you want, but that's just the way I've chosen to do it to be consistent with what is commonly out there. This pink box here basically says this single edge, this red edge, exists in the encoding twice, so it's redundant, but that's fine. It's not too much extra memory. So that's representation 1. This is one way we can represent a graph. And so to make that more concrete, I have a question I'd like you to ponder, which is suppose we write code that prints out the graph. So what it does is it says, we're going to start from vertex 0, go up to the last vertex, and then for each of those vertices, or sorry, for each vertex adjacent to vertex v, we'll print out v plus dash plus w, which basically will just print out all the edges in the graph. Okay. So in this case, I'd like you to sit down and think, well, maybe you're already sitting, but think at least, what is the order of growth of the running time of this if we're using the adjacency matrix representation? And 2 little sub-questions to think about are, 1, how much time does this adjacency method take? And how many calls are made to it? So I'll let you ponder that, and then I'll spoil it in a moment. So remember, I'm going to give you a little hint. The edge method is supposed to create an iterable of all of the edges. So if I call it with 1, it needs to give me an iterable that contains 0 and 2. Okay, so how long does it take to build an iterable? Well, what we have to do is we need to go through each of these elements, basically. So if I want to know what's adjacent to vertex 1, I need to look at this element, and this one, and this one to build the iterable, which will contain the numbers 0 and 2. So in the worst case, it'll be theta v. We go through each of these items here. In fact, it'll always be. It's not just the worst case, but every case. It will go through all of these and produce an iterable. That's what the adj method does. Now, how many times do we call that method? We'll call it v times. So once when v is 0, once when v is 1, once when v is 2, and once when v is 3. So if we make v calls to something that takes v time, the overall runtime will be v squared. Okay, and so if we think about what g adjacent, just to make sure that it's clear, the reason this really the fundamental idea this all boils down to is that when we call this adjacency method on the vertex 1, we'll get back 0 and 2, and producing this thing, this is an iterable, I just made up that notation, that will take linear time to produce. Okay, so let's talk about a couple more graph representations. Representation 2 would be, let's not use a matrix at all. I'm not going to use a 2D array. Instead, I'm going to have a set. And what will the set be? Well, it'll be a set of edge objects, and each edge is just simply going to be a pair of ints. So if we want to represent this graph, we could represent it as the set 0, 1, 0, 2, and 1, 2. Okay, and this is just, again, a made-up notation that represents a set of tuples of values. Now, this approach is not typically super popular. There may be situations where it's appropriate, but I'm going to just kind of move on. I'm just giving it as an example. We won't do a detailed analysis because I'm going to stick now with the third representation, which is the most common way to represent graphs in practice, usually. Not for all applications, but for most. So in this approach, it kind of feels like a hash table a little bit. And what we'll do is, for each of our elements, we're going to keep a list of all of the vertices that are adjacent. So in this case, if we look at 0, it has a list that contains 1 and 2. If we look at position 1, it's a list that contains only 2, and 2 is an empty list. Okay. So I think that representation's perfectly reasonable. Hopefully it makes sense. And so what I'd like you to do now is consider what's the order of growth of the running time for that exact same function from before that prints out a table. Is it v, v plus e, v squared, or v times e? And I'll let you ponder that for a little while. And in this case, what you need to do is think, how much time does that adj method take if I need to return an iterable? And how many different calls to adj will I make? So I'll let you ponder that for a short while. I'll look out the window, see how things are going. It's a cloudy day. Okay. So, how much time does it take to call adj? Well, in this case, assuming that we actually have lists, well, lists in Java are iterable. So in other words, if I want to complete this call, that is creating an iterable, getting a reference to an iterable, it's actually instant because I already have an iterable. This is the iterable. So that is theta 1 time. And how many adjacency calls do we need to make? V. Okay. So that doesn't really give us the answer yet, but I'm just pointing out these two pieces of information. There's a little more complexity here. I don't need that right now. Go away. So how many adjacency calls? It's V. So we're basically going to return 3 of these. So let's think about what the runtime might be in terms of cost models. So if we count adj as our cost model, the runtime would be theta v. In terms of units of time, if we assume that each call to adjacent is constant time, in that case, if that's our cost model, it's theta v. However, if we count prints, which is the innermost piece of the loop, we would say it's theta e, right? Because for every single edge in here, where e is the number of edges, we're going to print out 3 times. And we have a graph with tons and tons of edges, it'll be theta e. So the question is, which is it? Like, what's the better cost model? And it turns out in this case, well, we don't actually know whether or not the number of edges or the number of vertices will be greater. And so what we'll do is we'll say that the total runtime is v plus e. And the argument there is simply, okay, let's say I have a ton of, it looks scary, but it's actually pretty simple. It's basically this. If we have tons and tons and tons of vertices with very few edges, then the runtime will be dominated by simply returning that reference over and over. So I have 1 million items in my graph, 1 million vertices, and almost no edges. The runtime will be about theta v. It'll be proportional to the size of that list. Okay. Now, by contrast, imagine I have only a small number of vertices, maybe 1,000, but every single edge points at every other edge. Well, in that case, we have about 1,000,000 total edges because every vertex points at every other. So that'd be about 1,000 times 1,000. In that case, the runtime would not be dominated by v, but rather by e. And so this runtime with graphs is very common. You'll see it time and time again. This notion that, well, it kind of depends on the graph. If it is a sparse graph with few edges, it'll be theta v. If it's a dense graph with lots and lots of edges, that has many more edges than there are vertices, then it'll be e. And so we could say that overall the runtime will be theta v plus e. Okay. So this is something to get used to, something you'll see time and time again. And those are our basic representations.